Okay, let's do number 2 from the practice exam. So you can see what we're trying to integrate here is a rational function. So that means a ratio of two polynomials. So you can see there's a polynomial 2x on top and a nice factored polynomial on the bottom, which would be a quadratic if we multiplied these two things together, right? So whenever you have a rational function, you can find its antiderivative by using the method of partial fractions. So there are lots of different cases in general for doing partial fractions, but we are just going to do the very simplest case, which is a case like this, in which, okay, so notice that the degree of the polynomial on top is lower than the degree of the polynomial on the bottom. So this is x to the first power is degree 1 on top. It's degree 2 on the bottom. Okay, if that weren't the case, then you have to do polynomial long division and break the expression up. Alright, so it's nice in that way. It's also nice not only because it's factored into these two factors on the bottom, but also because these factors are different. So this is kind of the easiest possible case to do partial fractions. And what you do is, the whole idea is that you don't know how to take the antiderivative of this complicated thing, but if there was just some way to break this expression up into two simpler pieces, then you might have a chance. So let me write this like this. 3x plus 1 here. Okay, so partial fractions gives a way to break this up into these two pieces. This is going to be one fraction with just x plus 3 in the denominator and a as a number, and then there's going to be another fraction with just 3x plus 1 in the denominator and b is also a number. Okay, so we'll see when we get back to the integration stage that makes the problem easy. I mean, you can almost do these immediately in your head, right? What's the antiderivative of this? It's natural log of x plus 3, and this is 1/3 natural log of 3x plus 1. Alright, so all we have to do is find these mysterious numbers a and b, and so partial fractions guarantees us that there are numbers like that, and this is how you find them. So you want to multiply both sides by this. Okay, multiply both sides by the denominator of this fraction. And what happens when you do that? You get 2x, because it's cleared on the left. And now x plus 3 cancels with this x plus 3, and you get 3x plus 1 times a. Okay, plus. And now, you're multiplying this stuff times this, and what happens is the 3x plus 1 cancels, and you get left with x plus 3. You have x plus 3 times b. Okay, and now, frequently what you can do is plug in tricky values for x and kill one unknown and then solve for the other one. So notice that if I make x equals -3 here, if I make x equal -3, then this is going to become 0, right? Because -3 plus 3 is 0. On the other hand, the other stuff will just kind of be something, so this will turn into -6. And what is this? This is going to be -9 plus 1 is -8a. Alright, and so it's not hard to solve for a here, right? A is just equal to 6/8, and what is that? That's 3/4, right? Okay, so a is equal to 3/4, and now I want to try the same trick here. So what do I put in to kill a? You can write it down in an equation or whatever, but you can probably just see that what you need to put in for x is -1/3. So try x equals -1/3. Okay, then you'll see that 3 times that is -1, and that kills that, and so a goes away. Alright, so what happens when you plug in -1/3? You get -2/3 is equal to, so it's because 2 times -1/3 is this. Now this vanishes, which is the point, and for this stuff I get -1/3 plus 3 times b. Okay, so now we kind of have to go through this slightly tedious process of finding out what b actually is. So let me do the fraction here. So this is the same thing as -1, so -1/3, and then if I put these over a common denominator, this becomes 9, right? Okay, so here's b. This is the same thing as 8/3 times b. Now you can multiply both sides by 3/8. So you get 3 over 8 times 2 over 3, -2 over 3, is the same thing as b. Alright, and okay, so cancel those 3's, and you get that b is equal to -1/4. Right. So, not too hard, right? A is 3/4 and b is -1/4. So now the dream has come true. So this complicated thing that we wanted to integrate, we can now write it in this much simpler way. Maybe I'll copy these, I'll erase these and put back what they really are. So now we know that A really is 3/4 and b really is -1/4. Okay, alright. So now if you look at the integral, the idea is that instead of doing that complicated integral, you can just do this. Let me push this stuff down. Okay. Alright, so what we wanted to do in the first place was compute this, right, dx. Now since the integral splits over plus, this is two easy integrals, so here's one, and here's another one. Okay, so we wanted to figure out this in the first place. This is the main mission, is to compute that. But now we can just do these much simpler ones one at a time. Okay. So this is an easy exercise in U substitution. I'm not even going to use U substitution for this first one. So let's take the 3/4 out, and now you have dx over x plus 3. And your head should be telling you that this is a lot like the antiderivative of natural log. The only problem is this plus 3. But if we did substitution, the derivative of u would just be 1. Let's just go ahead and do it. I spend more time talking about it than it would take to actually do. So let's do that, and now du is equal to dx. And the integral that we have to solve is 3/4. And now this becomes du over u, and so we get 3/4 times natural log of the absolute value of u, and going back to x, this is 3/4 times natural log of the absolute value of x plus 3. Plus c, but we'll wait until the end to do that part. So let me push this down and deal with the other one. So the other one, maybe you would want to use substitution. I don't know. So here's -1/4, and we want to do the integral of dx over 3x plus 1. Okay, so let's just go ahead and do substitution. So let's make u equal to 3x plus 1, and now du is equal to 3dx, which of course means that 1/3 du is equal to dx. And let's reset things here. So I've still got this -1/4 outside. Dx has become 1/3 du, so I'll write that 1/3 here. And here's your du, and now the bottom is just u. And so what have we got? Put these two together and you get -1/12, right? Okay, and now when you take this antiderivative, you get natural log of the absolute value of u. And now going back to x, this is the same thing as -1/12 times natural log of the absolute value of 3x plus 1. Alright, so maybe now we should put it all together. Okay, so let's give the actual answer. Let me scoot, don't want to lose my stuff. Alright, so this is what the integral of this first one was, so let me cut that. Here it is. Oh wait, I haven't gone back to x at that point, so let me pull it up. Come on back up. There it is. Okay, so that's what I want. So this is the antiderivative of this first thing. Sorry, I'm making kind of a mess here. So that's the antiderivative of this first part here. Alright, and now let's put it together with this other thing. Okay, the antiderivative of the other part. So here's that. So let me take that away and put it up here. And look, that's looking a lot like the answer, right? That's the answer. Okay, so this is the whole thing. I missed that. Okay, this is the answer to the whole question. And of course, you could recombine these things using the laws of logs if you needed to for some reason. But I think it would look strange. You know, you force these back in as exponents or something. So let's just put a plus c here, and then we'll call it a day. So that's the answer. All right. Sorry. Stop.